Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. And for today's episode, I'm joined by Rob Nash from Petalite, and we're going to talk about Rob and his background and Petalite, the company, and the interesting work that they're doing now. And Petalite's a business you might not have come across before. I came across them a year or so ago and was absolutely fascinated that they seem to have come up with something genuinely new and revolutionary in the field of electric vehicle charging, which we will get into in the substance of this podcast. But thank you for joining us, Rob, and let's get started.
Thank you, Ryan. My pleasure.
We could just start by you telling us about your background, so how you got into engineering and how you came to be doing what you're doing today.
So that's a long story. So I come from a history of engineers. My dad was an engineer. My grandparents were engineers. So I was born into engineering, but also born at a time when necessity mounted. Now, it used to the Thatcher's years. We came from a poor background. So if I needed anything, I had to build it. So TVs, I had to repair. Bikes, I had to scrounge bits and build together. So from a very young age, kind of mother is the nature of invention came around. So I ended up building bikes, repairing TVs, cars, you name it. When friends had a problem, I used to fix it. Fix the butchers, weighing machines, that type of stuff.
Yeah.
Got myself some nice steaks.
Very good.
And then I went to college and I met a good teacher called Mr. Phillips, who was in physics. And he got me involved in electronics and kind of software. I remember the one day I was repairing TVs and I shorted out the HV tube and took out the chips on the circuit breaker, which was a lesson I learned. Electricity can be quite dangerous and fun at the same time. I was also brought up at the time when the personal computer came out. So, Sinclair, the Commodores. So Sinclair Spectrums, Commodore 64, 16s, Amigas, all that range. So right time, right age, right background to be really into engineering.
So a child of the 70s and 80s, if I had to guess.
Yes. So I was born in 1969 when the Apollo 13 took off. I don't know if that was an omen of people trying to leave the planet. So I was
they knew you were coming.
Yeah, I was built in that era. And so I was the first one in my family to go to university. So I'd done A-level maths, physics and computers. And then I didn't actually go to university. I ended up writing software for an accountancy company that bored the hell out of me.
Okay.
Software was just boring. So I did video games, done software, was bored. A friend of mine said, Robert, you should really go to university. So I signed up to go to university. So, well, what am I really interested in? And you don't really know that. But because I was into computers and I wanted to build computers, I went to Birmingham City Polytechnic at the time that became UCE, and I got onto a really good electrical and electronic systems course, and that allowed me to do everything. So I did software that the university sold to companies for the Zytek Spectrum and QL that was basically a debugger for their software. But I also did power electronics and control automation. So I had quite a blend where, I just loved electronics. I love computers. During that course, I went to join a company called Davis Decade that was a small company that was at the point of going from analog to digital in terms of automation. And they wanted somebody that could bridge that gap. So they brought me in and I did everything from business development, design, implementation, test, commissioning, all the way through. And that wasn't just in electronics, it was in the mechanicals. Okay, it was in software, it was in safety applications. So I've got a really broad background of engineering. And out of that, while I was still at university, I was lucky enough to be given an opportunity to do a self-optimizing machine control algorithm that basically controlled a complex manufacturing line to take out all the delays to maximize production. Okay. So it did measurements, statistical analysis, and then said, well, actually, this is the optimal operating point.
Machine learning early?
It was machine learning, effectively. And lucky enough, I then got awarded part patent through Davis Decade. I wasn't into patents. I was something new and basically increased productivity by 240% and minimize downtime. Just because, if you're feeding material and the material is heavy, it takes more time to feed it into place. As the material gets lighter, you can feed it quicker. Okay. And so machine learning, statistical approach, increased productivity. So I got a patent. I then probably did the worst thing. And when I demonstrated it at the end of my degree project, the guy said to me, yeah, this is not going to work. It's overcomplicated. And then I showed him a report and he said, well, what do you know? It's actually making money for the company I went to.
Yeah.
Okay. So I fell over to professor at that point. So I went into that area. So I was always trying to say, if it can be done if physics says it can be done, then we can engineer it if we understand the maths.
Yeah.
Okay? So that's where I started. I then did the new range of products for Davis Decade, but the owner was quite comfortable, not wanting to grow, not wanting to push the company once I'd done this. So I found, actually, I need another technical challenge. That technical challenge was to see how far I could go academically and practically in terms of my engineering capability. And at that point, I looked around and I saw a company called Zytek. And I don't think people know Zytek. And I joined up and there was like a load of boffins, a load of geeks. I felt like it was Santa's lair. It was brilliant. And I thought, you know what? I've won the lottery. If I get offered a position here, there's really good engineers that I can learn from. And luckily, a guy called Aidan Gregory gave me the opportunity. And so I then went to work with people from Lucas, people from TRW, that were, the people in the tweed jacket engineers. They were the geeks. And I learned off them absolutely everything. And it was brilliant.
So is that the Zytek that was sort of Formula One engine controller fame?
Yes.
Yeah.
Yeah. So Zytek at the time when I joined were moving from Formula One engine management that they did for the Bentley and for Totem Pole. Because I don't know if you know Zytek. Zytek was a group of good engineers that came off the ECU for the car. They did the first electronic control unit for cars. It was implemented in Totem Pole and it allowed Ayrton Senna to win the first Formula One race. Okay. But like all great British, then they weren't good money men. They didn't patent the idea, and of course everybody else took it over. They then took that technology and did it to Bentley. Okay, so they did the Bentley, they did the XJS 220 ECUs. But Bill Gibson at the time had a vision saying electrification's the future. Okay, so he invented a group or created a group that allowed us to go and explore electrification. And that was brilliant to me because I got back to computing and high power, high voltage design. So reverse engineered the Smart 451 to be the electric vehicle it should have been. Okay, so, and I picked up halfway through that project. That then got picked up by Mercedes at the time, that then employed us to go and produce the first EV vehicle for European sales.
Before the podcast, I said I thought we'd crossed paths somewhere before.
Okay.
My old business supplied and built telemetry units that were fitted to the smart EVs that went out on trial in the UK, and we spent time down at Zytek, and the cars were up at our place in the northeast of England, and that would be it.
Yeah. So that's brilliant. So when we started to do that, I started an Innovate project. I brought the company into an Innovate project called ITKEV that was integrated power electronics control. And that allowed us to develop all the simulation tools for the next range of control methodologies and implementations for the EV market space. And so we designed our first power module. I was quite lucky to be able to design our own power module. That was an experience. But out of that technology, we got approached by McLaren and HP at the time because they was getting into the first Formula One. And they said, guys, you seem to know what you're doing in EVs. Can you design our first KERS system? So we designed the first KERS system for McLaren, but we worked really close with HPE. We was employed by HPE. And that's my first taste of Formula One. And it was really interesting, the expectation, the pushing the boundaries, and the hard discussions and engineering challenges that you have to overcome it. And I'd like to say we taught HPE how to do KERS, because we did. But we did it that well, they decided, you know what, guys, you've done a good job, we've learned off you, we don't need you anymore. But I was part of a team that then basically brought KERS to Formula One. And our KERS system was air-cooled, half the weight of everybody else's, and didn't have a failure throughout the season. And I got to play some really good technology where you realised you had to develop the technology for the application. So we ended up playing with silver diamond composites, silicon carbide, advanced part class transfers. So we basically set the precedent on what the modern day electric vehicle inverter should be based on. And so we went through that stage. There was a couple of others, like we did Modec, that was based on the first urban electric vehicle delivery truck with a swappable battery. So we'd done the system for them.
Remember the old Modex, yeah?
Yeah, the Modec that got bought by Navistar. And I think it's Neo that's coming up with another idea that you can swap batteries. But at that point, Continental then got interested because clearly we opened the door to Mercedes. They didn't have that knowledge, so they bought into Zytek. But during that stage, we also got involved with Infineon. And hopefully most people know Infineon. And they started developing the hybrid pack 2, which is very similar to the power module that we started developing at Zytek. And so we supported them through the SMART program to finish off and validate the hybrid pack 2. And Infineon said to us that we was the first £1 million customer for the hybrid pack 2. We started and helped Infineon open up their power electronic modules. So we learned all this knowledge. Then after Formula One, I'm getting a little bit old here, we then did the first parallel hybrid truck for GM that was launched in the US, Silverado. We then took into Formula E, and we did Formula E in our system. Can't say who it's for, but our system won 3 consecutive seasons. Okay? And it's quite interesting, people saying, we can't believe you're beating us with old technology. And the reason being is because we knew how each part of the system worked, we could optimize it. Engineering should be equally spread. It's like a round balloon. But if you squeeze it too tight somewhere else, you put pressure in different areas of the engineering. So we had a really advanced team of software engineers, control engineers, mechanical engineers, safety application engineers. So, well, actually, guys, this is how we get more out of the sum of the parts and the whole. Okay? And at the time, so we won 3 years in the trot, and this is with old, not old technology that we'd optimized. We got dropped again because it became commercial then. They didn't want to push the boat to the next step. At that time, then we did some other sports cars. I moved into DC-DCs and fuel cell controllers. That then gave me experience about fuel cells management.
So was all this still Continental acquired? Did they acquire all of Zytek or just part of it?
So initially they acquired, I think, 19%. And it's really strange on how it happened. So Motorola wanted to develop an engine management system. They wanted to get into an engine management system, but they didn't have the software algorithms. So they bought 19% of Zytek for the software knowledge. And so I'll have to say I was not, I love Motorola because I used to write software for the 68000 because I was always anti the 86 family. Engine PC was like sucking a lemon for me. And so when Motorola that did the 68000 processor bought 9% of Zytek, I really wanted to work on that project, but I didn't get the opportunity. But the team that did helped develop the range of processors that went into new engine management systems. But then Motorola got bought by Freescale, if I remember correctly. Renamed, got bought by Freescale. Freescale got broken up, and part of that became an NXP, and Conti bought the other part. So all of a sudden, Conti thought, we own 9% of this company in England. What are they doing? Yeah. And then they realised they're doing electrification and think, okay, we'll now buy 50% of the company. So they put their stakes. And it's really interesting when a company has a 50-50 ownership. At that point,
if everyone's pulling in the same direction, it's fine.
It's brilliant. Yeah. So Conti said, well, guys, this has to be more now commercially viable. You can't just go and design the next Starship Enterprise. It doesn't work.
Yeah.
Okay. And as the technology,
killjoys.
Yeah, killjoys. Which is like doesn't compute to the engineers. So then what happened was, as the EV market matured, we have to become more commercial. It's all about series production. It's all about cost downs. It's all about different applications, usability. So Bill Gibson's kind of entrepreneur innovation was taking a more and more back seat within the business. And so then Conti decided they was going to buy the whole of Zytek. Okay. So they bought up the whole of Zytek, that then still allowed us to do engineering on prestige projects around the world to support their innovation, their customer base. So we've worked with the likes of Maserati, Ferrari, some others that I can't mention because of NDAs, and some that are currently in Formula One that I can't mention because they wanted the Zytek technology USP edge, but didn't want to know it's coming from Zytek, okay? Because it damages the brand. So they end up buying the whole of Conti. At that point, there wasn't really much more that I could do in the automotive. I'd done all the inverters. I played with silicon carbide. I played with DC-DCs, or not played, engineered, high performance and cost effective. So there wasn't really a challenge. It was just take what we've got, modify it, send it somewhere else. And at that time, I think it was about 2012, we had the idea of, how do we liberate the people to be able to freely charge their cars. So Continental, or I came up with a couple of others, an idea of this charge station. Okay. And we set up a big program to do it. And then all of a sudden, Conti pulled the plug saying, we're automotive. We don't want to do this infrastructure, which was a bit of a shame because we got Sony on board with their software. We got Yuasa on board with their battery technology. We had sites at Cardiff University all geared, and then Conti pulled the plug. It came evidence that, I needed to get back to my roots. I need to get back to innovation. I need to get back to designing something that actually moved us forward. And then that's where Petalite approached me saying, look, there's a challenge with this charging technology. Are you interested in coming in? And I looked at it and thought, this is a really good idea. I can make this from, research into a product that can be sold. But more importantly, it gave me the opportunity to train my replacements, to educate and mentor and coach high-performance engineers that are not frightened to take on the big challenges that we'll face. So I ended my notice as Chief Engineer at Continental, or KESH UK, and then joined Petalite. And I came to Petalite, and it's like I won the lottery again. There's a new technology with a new idea, a load of challenges. I thought, great, this is brilliant. So I took the challenge on that, got to build an engineering team, got to develop the engineering team, got to put in all the processes to allow us to engineer in a very flexible, agile way, as well as delivering the project.
So what's the origin story for Petalite? Where did they come from?
So Petalite came from a spin out of Aston University. So it was a group of engineers that was at Aston University, spent 8 years looking at, what was the real question that was preventing charging. And I suppose to a certain degree, they spent 8 years trial and error guiding to come up with a really good answer. But it was also a case at the right time, at the right place, because new technology off the back of the EV market was becoming commercially available to allow the new concepts to be realized, like silicon carbide allowing higher switching frequencies, more advanced magnetic material that allowed us to get more power dense transformers. So they realized actually with this technology now, we can simplify the whole processing line of conversion. So they can make the stages simpler, less stages, and those stages used more reliable components. But because of this method they chose, it had inherent advantages. Inherent advantages was power factor, phase balancing, okay, and hence efficiency. Also, the ability to scale the DC-DCs. Most control methodologies, and you get people that can argue one way or the other, but there's generally pros and cons. Voltage mode converters are generally more difficult to parallel. You need more engineering effort, you need more sophisticated control to get it to happen. But Petalite's current mode made it a little bit easier. So the ability to parallel the DC-DCs was easier with the SDC technology. And because that made it easier, you can actually then make it more modular by using smaller conversion stages. And that then created greater redundancy, greater scalability, that resulted in greater reliability.
And did you call it did you say FTC technology or?
SDC, so Sigma Delta.
SDC technology. And what does that stand for?
Signed DC.
Okay.
Okay. I didn't come up with the name, but that's what they created, and you can understand where that name comes from.
Signed DC. Okay. Yeah.
Okay. So you've worked with electric machines.
Yeah.
Yeah. You understand?
One or two.
And so one or two. Are they still going around?
Some of them.
So the idea with electric machines is the balance. The three phases are balanced. Yeah. So if you sum all the voltages or all the currents, it should be zero. If you square a sine wave and the three phases, they should all end up with a DC level. So that's what SDC does. Effectively, we rectify the three phases and switch them in synchronicity to create a DC with very low ripple. Okay, and because we're using silicon carbide, we're switching them so quickly, the power factor is effectively 1, because we're using the input rectified signal as the modulating waveform for the current.
Okay, interesting. That's a power factor of 1 on a DC-DC is, that's amazing.
Close to 1. Close to 1.
Okay.
And the only problem you have with that is, because the way you transfer magnetics is at the zero crossing point of view, you get a slight discontinuation in the waveform. But advanced control techniques can remove that.
Right.
So because we're switching in the region of 50 to 120 kilohertz, the harmonics are nowhere close to the 50 hertz main. Because we're switching that quickly, it also means that we can effectively absorb or redistribute harmonics we receive. Okay? So we can clean up the harmonics that we're attached to. Likewise, the system takes more energy off the higher phase. So if the phases are out of balance, we naturally take more power off the phase that's lightly loaded and less power off the phase that's heavily loaded. So we start to rebalance the phases. So there's several inherent advantages to the system.
Yeah. I imagine there's a massive change in terms of the actual topology when you do that. Just sort of trying to think in my head of what sort of component set you need now or don't need. It's quite a simple design, actually. It's sort of very beautiful in its simplicity.
Yeah, keep it simple, stupid.
Yeah.
So in a normal AC to converter, AC to DC converter, you normally have a three-phase front end that does your power factor correction. So it creates a stable DC. And then you have a different topology to transfer it across the transformer, whether it's flyback, whether it's PWM, whether it's semi-resonance. But you really have a normal DC. In our conversion, we combine those into one. The power factor and the conversion is done in one stage. And that's where it simplifies it.
So you kind of got rid of half the components basically out of the...
Yes.
Wow.
Yeah. And the other advantage with that is that most of the original phase one chargers basically took an answer to a different question and adapted it to the problem they wanted to solve. So they ended up picking up IGBTs, old control technologies, high ripple current. So they need to use electrolytic capacitors that are kind of less reliable. Whereas Petalite, well, because we started from a blank piece, well, actually the problem is this. So we use silicon carbide with high frequency, we use phantom magnetics, so we don't need electrolytic capacitors for our filtering. We can use metal film or even ceramics, So we're starting to simplify, use less bulky components, use more reliable components. That means that overall cost of ownership is less. And of course, coming from automotive, and I have no money, no space, and it's got to last 15 years. I brought that with me, that kind of approach, And I remember a guy called Martin Fark said to me, when you build something, take a part off. If it still works, why did you fit the part? You've added cost and complexity.
Yeah.
So take stuff off until it starts to work and then put it back on. And that's mass production. Mass production is about how to do it in the least amount of parts with the greatest reliability and safety.
Yeah. The VAVE activity going on.
Yeah. And the thing about it is, SDC is just one USP in terms of what we're doing. It's just the core, the power conversion, but it opens up so many applications.
So presumably this initial concept, the team that span out of Aston, they presumably got some really good patents to protect.
Yes, a lot of patents.
Okay, so good IP base in the business. And then where are you kind of like rolling forward to what you're doing now? Where are you at now with that technology and what you're doing with the business?
So let's talk about the technology. So the technology is about to be deployed early next year at a trial site. So we will demonstrate 350 kilowatt charging using our modular design. So fast charge. And so we'll prove that technology. We then got, and I don't want to mention at the moment because it's not for us to say, 2 pilot sites with one of the biggest CPOs in the UK.
Okay. Yeah.
To demonstrate. To demonstrate the advantages of our technology. Okay. We're also looking to marry it with a company in the US with battery storage. Okay. So you talk about SDC, but it's converter. So our converter can take DC in or AC in. It doesn't matter.
Yeah.
Okay. It's agnostic. Okay. So in the first phase, we'll do grid to car, grid to battery, and battery to car. Okay.
Yeah. Okay.
The second phase goes battery to grid, car to grid. So we see it more as a charger. We see it as critical energy infrastructure.
That's interesting, especially
and it allows you to go off grid.
Because an awful lot of charging companies are deploying battery buffers at charge sites, or actually even there's a company in the US who have a line of rapid chargers who've got quite a big battery pack inside the charger to deal with all the problems with the grid availability. So batteries in the mix is quite a big thing, but you've normally got the battery system's kind of separate, almost like an isolated DC to AC system to the actual charging systems. You can integrate in that. You must be saving an absolute ton of componentry and cost and volume. And so for a 350 kilowatt charger, let's say, if you compared your technology to a conventional sort of telephone box sized charging system, what have you got any kind of ideas yet of what the savings look like in terms of volume and cost and weight and stuff like that?
It's a different costing model. So the answer is yes, but it's a different costing model. So the costing model is fairly interesting because we're targeting the same costs for comparable power from our competitors. However, we can spread that power to increase utilization across more charging points. So the Petalite system also has dynamic power management. So we can send up to, in 20 kilowatt blocks, power to one of 6 posts. So you have one car that needs 350 kilowatts and nobody else is there, you get the full 350 kilowatts. As soon as that car battery can't take 350 kilowatts, so you know what, I can only take 330, that 20 kilowatts is available to another one of those remaining 5 posts. And so we can scale and move in 20 kilowatt blocks our power between 1 and 6 posts. So we make a more availability and increase the utilization. So for the installed power, the actual power delivered to the car is greater. And for our algorithms, we can manage the charge of the cars to get the optimum charge based on the time.
That's a really interesting model. I mean, some people might not realize, but it's a very sort of big thing with charging parks where you have an installed electrical power capacity, and obviously you have a number of charging points that are at, say, 350 kilowatts. That's a good number to use because a lot of them are 150 kilowatts. And you'll have 20 on one site, for example. But the cars that turn up can invariably never use the maximum rated capacity of the charge points. So there are a few different systems about how you kind of shuffle that charge around to be able to sort of minimize your infrastructure costs and your kind of your cabinet costs and your installed power converter costs to give you the best sort of utilization level you can get at for the lowest overall total system cost. And that's where you guys are really targeting this technology, which is that's a massive area because it's just so inefficient. If you're building a charging park and you're putting 20, 350 kilowatt systems in, you wouldn't size it for everything working at 350 kilowatts all the time because very few cars actually would be able to take that power. And even a car that could take 350 kilowatts in theory can only take it for a fairly small part of the charging cycle. So it's not, it's just not practical to have like a 20 times 350 kilowatt capacity of the system because you're never ever going to be able to use it and utilize it. And you're doing something about that big problem.
Yeah. So the whole concept is we have things called power groups, and power groups are scalable up to 640 kilowatts. Okay. Those power groups can then feed up to 6 posts. So if you really wanted with a water core cable or a really high power cable, you could put 640 kilowatts to 1 point. But dynamically, we can move that in any blend we like between 6. However, we can parallel power groups. So any spare capacity of one power group can be sent to another one.
Yeah.
And on current installations, we could have up to 36 posts. So that's 6 times 640 kilowatts. So effectively 4 megawatts we can dynamically move. But the advantage is it's scalable. If we have an issue with a unit, it tells you which unit's going there. You can unplug it and plug another one in, so you don't lose the power station. Now, if we lose 20 kilowatts of 1 megawatt, what's that? No one will really know.
Yeah.
Because you said this station is never going to run at 1 megawatt all the time. So what we can do is optimize how much installed power you need and then maximize the charge of the cars for the throughput.
Yeah.
And that flexibility is different way of looking at it.
Yeah.
Because what we said is, we want something that's reliable, we want something scalable, we want something cost effective. And what we really want something to do is be able to give the maximum charge of the vehicle that it needs at the time. And so we do a high power site or a high power unit that has its own dedicated feed from a transformer. And then we do a low power